Okay, so let's continue discussion of the basic concept of pre-stressing. Okay, so we have a concentric tendon pre-stress only. So here you can see, here we have the cross section. Okay, so the circle here is the tendon, which is placed concentric. So you have put it at the inside of the cross section, and you can see on the right side, this will represent the stress, which is compression, so that is negative P over A. So negative means compression. So you have the stress for concentric tendon and pre-stress only, okay, is negative P over AC. AC is the area of concrete, base times height. So yeah, again, compression is my. Okay, next, let's add the self weight. So obviously the beam have weight. So as you can see here, you have the cross section, concentric tendon. So the stress of pre-stress only is rectangular, negative compression, and then you can see here we have positive at the bottom and negative at the top. So it means that this beam is bending due to the self weight. So therefore positive at the bottom, tension, negative at the top, compression. So presumably it will be rectangular. So if the goal is to reduce the tension at the bottom, so writing the formula, so we have F raised to T, or the stress at the top, is equals to negative P over A minus MC over I sub G. So I sub G is the gross, meaning you are considering the entire rectangle cross section. So you did not reduce the area of the tendon on the computation. And F sub B, or the stress at the bottom, is negative P over A plus MC over I sub G. So yeah, stress at the top fiber. So stress at the top, so here, stress at the bottom here. So stress, so C is the distance from this CGC, or the center of gravity of the concrete or the steel, up to the top fiber and the bottom fiber. So for section that is not symmetrical, the value of C will be different if you measure from the neutral axis to the top, so we call that as C top, and then from neutral axis to the bottom we call that as C bottom. On the previous equation you can see here positive and negative. Okay, so positive and negative. When you fact, okay, negative negative, so positive, negative positive, negative. So again, CT and CB are distances from the center of gravity of section or the CGC line to the extreme top or bottom. Extreme top and extreme bottom. So next is the prestressing plus self-weight. So the beam self-weight may cause this M sub D or the dead load. So you just simply add negative MD over ST at the top because it will cause compression at the top, and at the bottom it will cause tension. So that is the idea. Okay, so here we have the orientation of eccentric pre-stressing tendon. So you can see why is it we have a different eccentricity as the section from the support to the midspan, the eccentricity is increasing. Okay, so at the support you can see that at the ends there is a small eccentricity, but at the midspan there is a big eccentricity. So it simply means that the pre-stressing tendon will cause a moment that will counteract the moment caused by the loading, since the basic principle for this simple beam, the maximum moment is at the midspan. So therefore, maximum moment of pre-stressing will be obtained if we put the highest eccentricity at the midspan. Easy. Okay, so at the support there is no moment. So we have this, we call this as harping, and this one is draping. So for harping, usually this is for concentric, and this one draping is for uniformly distributed load. So as mentioned here, so pretension for this type and for post tension is draping. Okay, so there will be other loads to be considered. So we have the M total, or the total gravity loads. So self-weight, superimposed dead load or the flooring, and dive load. So therefore, the equation, instead of m sub d, it will become m sub t. Okay, so let's move forward. So here you can see this is not symmetrical on the x-axis. So therefore, the value of the C top and C bottom is quite different. So there is the eccentricity. Okay, the tendon is far away from the neutral axis. So initially we have the negative P over A, PI over AC. So meaning there is no losses yet. Okay, because sooner or later there will be losses of pre-stress. To compensate for the eccentricity, so we introduce the PIECT and PIECB. So at the top, at the bottom, so you add them. So negative, positive, it will be a difference. Negative and negative, it will go wider. Okay, so this is what we got from the previous slide, and then we will introduce the self weight. Okay, so again, this means at the top, okay, compression. At the bottom is tension because of the gravity loads. Then you add them up, it will narrow, and then at the bottom it will also narrow because different signs, compression and tension. And then fast forward, we have this. We're going to add the service loads. Okay, so again, same orientation. At the top is going to be compression, and at the bottom is tension. Okay, so different signs. So this is compressed, and then, or rather, this is tension and compression. Okay, so what do we get here? So there is compression here, and then we have tension at the bottom. Okay, next is the C-line method. Okay, this is what you call the line of pressure or thrust concept. So we analyze the beam as a plain concrete elastic beam using the basic principle of statics. So in the figure, as you can see here at the bottom, okay, so this is a configuration for reinforced concrete. So there is a couple here separated by distance A. Okay, so if you're done with RCD, you're probably familiar with that. But here in pre-stress, okay, so they are concentric or concurrent. So there is no loads, so you have couple in pre-stress, no loads, they are concurrent. Okay, as the loading increases, what happens? So it's on the RCD side, it does not change, but on the side of pre-stress, it increases. So we have A. So the pressure goes up. Okay, as a result of this additional loading. So that is to maintain the balance. And then we have here, when we finally have the service loads, the total loads, okay, the reinforced concrete never changes. And then finally for the pre-stress, it will have the final value of A. Okay, that will this couple will counteract the moment caused by this load W. So meaning here small a means small moment due to the load, small loads. Big loads, big A. So you need a bigger value to create a bigger moment. So from there we can say that we have this moment, the compression times the A, or simply the couple, and from that, okay, so we need to compute this value E prime, which is equals to A minus E. So A minus E. So how do we get that? We get the value of A from this formula, which is A equals M over T. So A is arbitrary, so it depends on the moment. So big moment, big A, small moment, small a. And then you apply on the formula of E prime, and then what you're going to do is you just simply substitute the values. So we have negative C over AC, meaning the compression, minus CE prime, CT over IC. And at the bottom, CE prime CB over IC. So in the final form, in the formula, we just simply use PE. PE means we have the effective pre-stressing, so the losses were already deducted. So if we are at the initial stage, we use the PI or P initial, but if we use the PE, that means there is losses already. Okay, then again, looks familiar, so you just simply substitute IC as AC over AC times R squared, and then you will get this F top and F bottom as your formula. Yan, upward force and the drape, uniform upward force. Okay, so happens. So you have the imposed load, and then the load by the pre-stress will counteract. So it is sort of trying to balance the force downward by force upward. Okay, so with derivative for x is 0, so we have y is 0, c is 0, the derivative is 0, b is 0. For x is L over 2, your y is equals to a, your a is equals to 4a over L squared. Okay, then the intensity of load, so using calculus, equals to t second derivative y over uh, the second partial derivative of y over partial derivative of x squared. So substituting that, so what do we get? So that is actually the a, which is the second derivative, or the second partial derivative for the parabolic function. So that will give us 8ta over L squared, where T is the prestressing force. Okay, so we transpose that, and then we get this value. T is equals to QL squared over 8a. TA is equals to QL squared over 8. Thus we get the WB, which is the balancing load. Okay, it will be the balancing load. Okay, so using this diagram, so we have this excuse me, the WB and the WB, downward and upward, so it will balance. Okay, and that will give us this value of A, which is the distance between the couple, the C and the T. Okay, so with that, we can use the formulation for the stress at the top and at the bottom, which is negative P prime over A. Okay, so that is at the midspan. Because of the load balancing equation. Okay, so when we impose the load that exceeds, so there will be exceedance. So because of that, there will be unbalanced load, WUB. So that is we could have this unbalanced moment, MUB. So therefore, since as mentioned earlier, because of the balancing load, we have this P prime over AC. Okay, so the imposed load will obviously disrupt the balance. So therefore, you will add and subtract or add the unbalanced moment. So for the top, negative P prime over AC minus MUB over S top, section modulus at the top, and F bottom negative P prime over AC plus MUB over SB. So S section modulus at the bottom. So P prime, what is P prime? P prime is actually the effective pre-stressing force